Hi, I hope you're enjoying the book. In the book, I explained how Maxwell's equations describe a symmetry between electricity and magnetism. But is it a perfect symmetry, or are there slight differences? Let's find out. The first of Maxwell's four equations states that if we have an electric charge, then that electric charge will give out an electric field. And the amount of electric field will be proportional to the amount of electric charge. So that makes a lot of sense. For example, if I have an electron, that electron has negative electric charge, got a little negative sign in there, and that then gives out an electric field. So we can consider the electron as being the source of the electric field. What happens then is if a positively charged particle comes into the vicinity, then that positively charged particle will interact with the electric field in its immediate local vicinity, and that will result in it experiencing an attraction towards the negatively charged particle. So opposite charges attract. But what I really want to emphasize here is that we can consider the electric charge as being the source of the electric field. Now, can we say something similar about magnetism? Could we ever have a piece of magnetic charge in the same way that we can have a piece of electric charge? Well, let's find out. Because here, I happen to have a bar magnet. It's rather flexible, but never mind. Here's my bar magnet. It's got a north pole and a south pole. And the field lines of magnetic field always loop around from north pole to south pole. You can see this if you put iron filings onto a bar magnet. So you always get those loops from north to south. So could we consider the North Pole as representing a piece of magnetic charge, a piece of north magnetic charge? And could we consider the South Pole as representing a piece of south magnetic charge? In that way, the field lines, the magnetic field lines, would be coming out of the piece of north magnetic charge, just like we saw the case with electric charge. So how can we isolate a piece of magnetic charge? Well, I can do that because I've got a pair of scissors. And with my pair of scissors, I can cut my bar magnet into two pieces. And there you have it. I have a piece of north magnetic charge and a piece of south magnetic charge. And because these are single poles, we would call them monopoles. So here we have a magnetic monopole and another magnetic monopole. So just like with electric charge, we can consider these as being the source of a magnetic field. Problem solved. But of course, this isn't what happens. What actually happens if you cut a bar magnet in half, you get two more bar magnets. And each bar magnet has got a north pole and a south pole, and a north pole and a south pole. And once again, the field lines loop around from north to south. So you can never have a magnetic monopole. There are no magnetic monopoles in the universe. That's a fascinating question. So, when we consider the field lines looping around from north to south, that's interesting, because if we have a bar magnet in a volume of space, you can always tell the amount of field lines leaving that volume of space will be equal to the amount of field lines coming back into that volume of space. So the total amount of magnetic field will be zero. And that explains Maxwell's second equation, which says that the net amount of magnetic field in any volume, leaving any volume of space will be zero. Thank you.